Okay, so in the last video, we talked about a recap of ridge regression. And now I want to talk about what will seem at first to be completely separate, but we'll actually see how this idea of regularization will come back in class today. About this idea of feature selection, which is at a high level the case when you have many, many features, maybe millions or billions of features, and you want to somehow select a small subset of them that are somehow the most important, whatever that might be. So somehow reducing the number of features you have to something that is the most important thing. So you might wonder, why would doing that even help us? What's the point of removing features? Well, why not just use them all? Well, there's a few reasons why reducing the number of features can be very helpful. Namely, the one we've already talked about is using more features tends to lead to models that overfit. So if you use lots and lots of features, you might end up with a model that's very complex, one that has the ability to overfit. Also, sometimes comes at the cost of interpretability. If I have a model with 2 million features, I now have 2 million coefficients I have to look at and interpret. And it can potentially get really complicated if the features or overlap in any way, because we talked about we need to be able to fix all other features except one in our analysis. So sometimes when you have just so many features, it makes interpreting the results of your coefficients very difficult. And then finally, one reason to not use lots of features is efficiency. That if you have lots and lots of features, say like you're using DNA data and you have a feature for each gene, then you need to learn one coefficient for every gene, and there are a lot of genes, which then means your training time is slow because you have to learn all those coefficients. But then also when you make predictions about new examples, that also is going to take a long time because remember, even though this notation for making a prediction is quite compact, it's really this do the sum over each coefficient times its corresponding feature. And if you have 10 to the 11th coefficients, that loop to sum all those up will take a long time to run. And so we'll find that in general, you can yield much more efficient predictors if you can guarantee that your coefficients are sparse, that you somehow selected the most important feature. What does sparse mean? It means most coefficients are 0. So if you have this model with millions of features, but you can guarantee that only a few of the coefficients are non-zero, meaning all of the other coefficients are 0, you've now yielded a sparse predictor, one that has mostly 0 coefficients. And that can now help with complexity, interpretability, and efficiency because you could just skip all of the features that get chosen to have coefficient 0, since 0 times any feature value is just 0. You don't need to include it in your sum, and now you have a lot nicer model to work with. So we'll talk about one strategy for going about trying to achieve sparse coefficients using regularization. We'll talk about that in class. What I want to talk about in the rest of this video is one, some examples of why we'd use feature selection, and two, show a very kind of computational approach for trying to assure what's the right set of. So namely, let's first talk about some examples of why might I want to use feature selection, or why might I want sparsity, meaning only a few of the coefficients are 0. Well, if you take our case study example of housing prices, knowing just a few of the potential many features you might use, which ones are somehow the most important, can be really helpful in interpreting what determines the price of a house. So if you have all of these inputs that you might use as features available, but somehow you have an algorithm that tells you these ones I've highlighted in purple are somehow the most important, whatever that means, for determining house price, you can now focus your analysis on those. Or it helps communicate because now you can talk to homeowners or home buyers that these are the most important things that affect price. And that can help them understand a more very, very complex environment that is the housing market. So being able to reduce the amount of data you're using down to the most important bits is a very useful tool for communicating. And in the cases of housing, it might not be super clear why you need that. All of the features here are somewhat interpretable. Like we can understand what dryer or washer means. And so maybe it's not that too much work to just look at all of the coefficients. But when you get to a lot more complex examples, like brain imaging, the number of features you have available and just don't quite work in terms of trying to interpret them. So here's an example of trying to look at a brain scan using your favorite brain imaging technology. And you're trying to identify how or what brain activity controls some response. In this example, I'm using how happy or sad you report feeling at that time. So these brain imaging analyses generally put someone in a brain scan or in a machine that does a brain scan, give them some sort of stimulus and ask them for their response, and then correlating brain activity with that response or that stimulus. Now here, you can imagine that the number of data inputs you have is quite large. A picture is really just composed of a bunch of pixels. So each pixel, each tiny little square in this image, is a measurement of brain activity at that region. And so your entire input is all of these possible pixels. That is a lot of pieces of information you have available. And if you just train a regression model that weights them, the coefficients you learn are going to be quite complex, very hard to understand, and hard to interpret to say, like, the amygdala or whatever region of the brain controls happiness was the one that was active here. Neuroscientist, I don't know how brains work. If I was wrong there, don't flame. So what would be nice if we had a model that would tell us which regions of the brain or which regions of these measurements were the most important in determining this happiness. So it'd be nice if we can have feature selection built into our model selection or the model itself. So to start us off with our discussion before we get into class today, I want to start with an example with housing prices, talking about if I have this set of 8 possible features, what is the right subset to use? So should I use 1 feature or should I use 4? And if I want to use 4, which 4 are the right 4? And so I'll talk about an approach right now that we call the all subsets approach. So looking at every subset of the features to determine which subset is. So we start off with a baseline that says, well, what would happen if I use no features? So if I use 0 features, I'm not allowed to use number of bathrooms, I'm not allowed to use number of bedrooms, I'm allowed to use nothing. We call this baseline the noise. We're assuming here in this model that each yi just some noise. You can imagine that this model will not do very well on the input data, assuming there is some true relationship between some of these features and the price. And so this noise-only model might achieve really bad error. So we might have, in the case of looking at training error, some pretty high training error. Okay? So now that we have this one model under our belt, let's try another. What we'll do is we're going to consider every model that uses just 1 feature. So here, I'm going to consider at first the model that just uses number of bathrooms. So here I'm using yi. I should put w path plus some noise. I'm assuming it's the model is using number of bath. Okay. And then I try this again with number of bedrooms. I fit that model. And then I try square foot living. And then I try square foot lot. And I try every possible feature I can use, training a model only using 1 of them. And I just keep going over and over again, trying every model that uses 1 feature. So sometimes I describe this as the best model of size 1, meaning I'm using 1 feature. In that case, if we're doing that, you might find that square foot living had the best training error. And so we might indicate that if you're restricting yourself to 1 feature, square foot living might be the most informative because it yielded the least training error. There's a few qualifications there that we'll talk about in a second, but this is generally what you might do. Say, if you're limiting yourself to just 1 feature, square foot living decreased the error the most, so it might be the most useful. But there's no reason to necessarily stop yourself at 1 feature. You might consider all pairs of features, so all models that use exactly 2 features. Maybe number of bathrooms and number of bedrooms was the best pairing, but in reality, you tried all combinations. Square foot living and year built, waterfront and floors, And after training all pairs of features through a model, you might find that number of bathrooms and number of bedrooms was the best. So if you restrict yourself to 2 features, those 2 might be the most indicative of the price. One thing to note in this one example I've just done, no, I said for if you limit yourself to 1 feature, square foot living was the best. But if you limit yourself to 2 features, number of bathrooms and number of bedrooms were the best. This is entirely normal and can happen quite often in practice. For example, maybe number of bathrooms on its own is not very useful, but in combination with number of bedrooms, those together could be very informative about price. But if you limit yourself to just 1, maybe they on their own don't contain much information. So it's entirely possible for the best model with 1 feature to use square foot living, but the best model with 2 features to use number of bathrooms and number of bedrooms. It's all about how these things work together. And so there's no necessary requirement that the best features are nested, that the best feature of size 1 is going to be a subset of the features of size 2, etc. Right? There's no guaranteed relationship. But again, there's no reason to stop at 2 features. We could try 3, try the best subset of size 3, try the best subset of size 4, the best subset of size 5, 6, 7, and 8. Going up to the subset of size 8 of these 8 features is just all 8 features. And you can see here, there is this relationship between the number of features and the training error we occurred. So as we increased the number of features, we decreased our training error. The more and more features we used, we got lower training error. So my question to you, I want you to try this out for a second, is do you think the same relationship is going to hold for the true error, the error it would occur in the future? So take a second. What do you think the true error would relate to the number of features? Just go ahead and pause the video, and then once you're ready, you've taken this down in your notes, what you think, we'll talk about it. Okay, so let's try this out. So if I was looking at the true error, you might imagine that a model that used no features would incur quite a high true error. It probably won't do very well in practice. But even though the model that uses 8 features has very low training error, remember we said the more features you use, it's possible to be overfitting. And so low training error here might mean the model is overfitting itself to the training set and might not do well in the future. And so you'd see actually in practice that as you increase the number of features, you see our normal kind of error curve where training error goes down as you use more complex of model, and test error goes down for a bit, but then starts increasing again. Or sorry, true error, which we can approximate with test error or validation error. And so you might actually be interested in choosing a number of features that kind of do best in the future. So just maybe trying to get this estimate of best future performance. Maybe 5 features is the best rather than 8. Now, this approach is we call all subsets, because what we've done here is we've tried every possible subset of features to try to determine which one's best. Now, to determine which subset's best, you have a few options. You can use a validation set, find the subset that uses the best validation accuracy, or maybe using cross-validation, which is a very similar approach. And then I also list option 3+ is there is a whole field of research going into feature selection and coming up with quantitative ways of determining how good features are. There are other metrics you can use that try to penalize model complexity, like the BIC or Bayesian information criteria, or many, many others. We're not going to talk about this in this class. They're interesting, but they're a little bit too complex. But there are lots of things people try to do to try to determine what set of features are right. And for our part, we'll really just focus on validation or cross-validation. But there are many other approaches that. Now, this is where I'm going to leave us off for today in our video, but we'll pick up in class doing a recap of this. In particular, I want to focus on where this approach of trying all subsets might fall a little short. We'll talk about what is the actual efficiency of this algorithm, and we'll see that it's actually not that great in practice. We'll explore what this efficiency means and some alternatives in class for today.